Hi, and welcome back. It's time to resume our discussion of the relation of predicates inside MonadDB. Okay, so it's time to dig a bit deeper. We have been discussing the things at the SQL level and then at the mul level. Now let's look inside the implementation of the mul operators that are relevant for the evaluation of predicates. In particular, the theta select operation that was at the core of the explained mul program for our query Q7. So how would theta select look like internally? So that you don't have to do that, I went digging in the thick layer of C macros that you will find if you open up the MonadDB sources. It's really ridiculous and remarkable, the layer of macros and code rewriting that happens inside the source of MonadDB. But if you dig deep enough, then you will find the core of the implementation of the theta select operation of this mul operator. And what you will find there is this routine and this particular loop inside the routine that we will have a look at. So we are looking at the implementation of the mul theta select operation that receives a column of values. Let's assume that this is a column of int values. And if you look at the associated parameter here in the theta select implementation, it's indeed a pointer to int values. This is the pointer to the input vector of int values in this case. We will compare these elements in the vector using this comparison operator. That could be equality or the greater than relationship. Any operator would be okay here. It's not really relevant for the discussion. And we would compare the vector elements with this value v of type integer. Okay, and we find that here in the signature of the theta select C implementation again. So that would be the input to the theta select. And the output would be the selection vector, of course, which is the expected outcome of a MonadDB filtering operation, a selection vector. This is also a vector of integers, but recall, this is a vector of OIDs or of offsets into a but. This is the result of the theta select. There's also an integer return from the theta select, but it's only the number of qualifying rows. So this is interesting information, but not in focus currently. Okay, so how would we go about that? We would first inform ourselves about the number of rows that are in the input vector. Okay, so let's assume that this is available in size. We will use an integer I here to point into the input vector. So I will start at 0 and then will be incremented by 1 in each iteration of the loop until we hit the end of the input vector. Okay. We will also use this out variable, which will be a pointer, an index into the selection vector, into the output. So we will increase out whenever we found a row that has actually been found to qualify regarding the comparison operator theta. Okay, so we start at the zeros offset of the selection vector. We will fill the selection vector from its start. Okay, so if we then enter the loop and the iteration, of course, the first thing that we will find is the prominent if then else, the condition that really makes up the semantics of a filtering operation. Does the current vector element satisfy this particular condition regarding the operator theta and the other literal constant v here? Okay, if this is the case, then the row at offset I is indeed a row that has qualified. This I is being recorded in the selection vector. Okay, and to make sure that the next I, the next OID, will be appended to the selection vector, we will then increase the out offset here. Only in this particular case is out indeed increased. Otherwise, we would just not enter this particular piece of code, this branch, and otherwise we have found a row at index I that has not qualified, and its index will not be recorded in the selection vector. Okay, This is all about the theta select. It's again a very tight loop, a super tight loop. And if you like, you can just take this routine, add a little bit of prelude there, and throw it into the godbolt.org site that I've shown you earlier, where you can see the code pane and the assembly pane side by side and compare the assembly code that has been generated for this very tight C loop here. And you will find it's really a handful of instructions that will fit in any instruction cache of any CPU out there. Super efficient. What's not so efficient about this is actually this here, this branching that is implied by the if then else. All right, so let's have a closer look at this. This is a control flow branch, so either we enter the body of the if, or we just jump around it or will not enter it. So the CPU actually cannot tell whether we will enter this particular piece of code or if we won't. And that's actually a core problem for a modern CPU. Most of these CPUs are so-called pipelining CPUs that execute more than one instruction at a time. We will have a closer look at this, but the control flow branching, the unpredictable control flow branching in particular, can be a real challenge for modern CPUs because it will disrupt their very efficient pipelined evaluation of instruction. Okay, so this is actually a problem for all branches, not only for those initiated by an if then else, but also, for example, by for loops, which sometimes re-enter the loop at the top of the body of the loop or may exit the loop. This is also a control flow branch and also constitutes a challenge for modern CPUs. But our focus currently is on the if, the core of the semantics of the theta select operation. Okay, so how does instruction evaluation inside a modern CPU look like? It's really performed in stages. So let's look at this. Please note that the time in this particular diagram is running from the right to the left. So that's a bit unusual, but it made the display of this diagram a bit easier. Okay, so time progresses from right to left. Okay, so let's only look at instruction I here, at this very first instruction. More focus, please. All right, so this is the evaluation of the instruction number I. Okay, its evaluation is performed in a number of stages. Okay, first we would access the memory of our computer to fetch the actual instruction, to fetch it from memory into the instruction cache of the CPU. All right, that would be a memory access actually that's happening here. First stage of the evaluation of instruction I completed. We would then decode the instruction decode ID. We would decode the instruction, look at the opcode, and try to find out what operation is actually to be performed here. All right, it's very typical for such a pipeline CPU evaluation that at this early stage also branch flags are tested. So at this early stage we can already decide if the particular instruction that we are decoding is a branch. Okay, then we can look at the branch flags, at equality or overflow flags or whatever, carry flags, and decide whether this particular branch shall be taken, yes or no. This is decided in this ID stage. In the next stage, in the EX or execute stage, we would perform real computation, probably some arithmetic that has to be performed. All of this would happen in the third stage, in the EX stage. Once we've done that, we would enter the MEM stage. Now that we've performed some computation, probably computed the addition of some offsets or something, we have an address available. We could use that particular address to access memory, to just read or write to memory and perform loads and stores, for example. Okay, the result of such a load, for example, would then be written back into a register of the CPU in the last stage, in the WB stage, in the fifth stage of expression evaluation. Okay, that would complete the instruction evaluation, I'm sorry, that would complete the instruction evaluation of the ith instruction of our program. A pipeline CPU will start the evaluation of the next subsequent instruction at slot I+1 or address I+1 already while the first instruction is still in flight and still in processing. You see that at this time step already we will start to fetch the next instruction while the first instruction still is in its decoding phase. All right, so starting from this point in time, 2 instructions are in operation in our CPU at the same time. All right, and of course the scheme progresses. Once the fetch for this instruction is done and we enter the next slot of time, the third instruction at address I+2 would be fetched, and we would start its 5-stage evaluation cycle already at this particular point. So at this point, there is even 3 instructions in operation at the same time. Okay, continuing here, we would now like to start the evaluation of the 4th instruction. The CPU has enough silicon on board to evaluate many of these instructions in parallel, actually. Well, at this point there is a slight problem here. We would need to start the instruction fetch for this instruction at offset or at address I+3. Instruction fetch means accessing memory, okay, reading memory. The CPU can only read and write memory in one such stage at a time. As you can see, the very first instruction that we've already started some time ago is currently in its mem stage, where it would read and write memory. So we would use the read and the memory bus from CPU to the RAM to satisfy this mem request, to implement this mem stage of the very first instruction. And we would have to stall this instruction at offset I+3. It will have to wait until its instruction fetch can actually be started one cycle later. Okay, so that's unfortunate, but it's a must. We have to postpone the evaluation of this instruction and therefore disrupt the nice pipeline flowing that we've seen here. There's a jump here in the pipeline before we can then resume the whole thing. Okay, so that would be pipeline evaluation of instructions inside modern CPUs. And well, the nice picture is disrupted a bit by the necessity to have these stalls here. Okay, because there's some resource contention inside the CPU. All right. So that's the picture of instruction evaluation in modern CPUs. How is this related to branching and the evaluation of selection conditions? Well, as you've seen on the other slide, this is related to the evaluation of the outcome of a branch test. Okay, so in this particular pipeline, the outcome of a branch test is known once this instruction at slot or at address I has completed its ID stage. At the end of the ID stage, we know that particular branch flags have been set or not set, and at the end of this stage, at this point in time, let me mark it. At this point in time, we do know whether this branch instruction will take the branch or whether it just fall through and will not take a branch. At this point, the control flow decision can be made. Okay, this is unfortunately a bit too late for the instruction I+1. We have already had memory access here and have completed its IF stage. This is the IF stage of the instruction in slot I+1. This has already been fetched. We have already invested memory access for this particular instruction. I'm sorry about that. For this particular instruction, only to find out maybe that the branch at slot I has decided to indeed branch. We will not fall through and we will not evaluate the instruction in slot I+1. So this fetch has been, this memory access even, has been in vain. All right. Indeed, we need to jump to the jump target of this branch instruction, and the jump target might be located somewhere, maybe at slot J. If this is the jump target, then a completely different instruction would need to be fetched and then decoded and so on. So all of this is an effort that was started but has then been found to be in vain. And that's unfortunate because it again disrupts our nice flow of the pipeline. So the nice flow of the pipeline is disrupted again. All right. Okay, so such pipeline flushes, we have to remove this particular partially evaluated instruction, have to remove it from the pipeline and make sure that it has no effect on the running program. Such pipeline stalls and such misfetched instructions are indeed a significant cost factor in the evaluation of pipelined instructions. All right. So this is really something that we would rather avoid. If we only knew the outcome of the branch already at this particular point. If we would know the outcome of the branch at this particular point, we would be sure whether it's okay to fetch the instruction at slot I+1 or whether it's time to branch and fetch the instruction at address J. All right. But knowing the outcome before we do the decoding and have tested the branches would be a miracle. We would have to have the ability to predict the future. And this is indeed what modern CPUs try to do. They try to predict the outcome of branches before we are actually in the position to evaluate the branch flags. Okay. And such branch prediction is based on multiple techniques. The main two techniques inside modern CPUs that are in use here is history and heuristics. Okay, so history says if a branch at a particular address I, for example, has always been taken in the last few encounters of this particular instruction at this particular address, then it's probable that this branch will be taken again. So the history of the branch outcomes say this has always been taken, this branch, so let's jump to, or let's fetch the instruction at the jump target J, because we try to predict the future from looking at the history. That would be the branch prediction in place here. If that branch has not been taken in the last few cycles, then we would just fall through and predict that it's okay to also fall through again this time and fetch the subsequent instruction at slot I+1. Okay, all of this, of course, might go wrong. All of this predicting the future from the history might go wrong, but it has been found that branches in typical programs are indeed very predictable. Some of the branches at least, are very predictable. There are notoriously hard to predict branches, and we will later construct situations in which we try to trick the CPU and lead it astray, so that all of its prediction effort is in vain. But in well-natured programs, or in most of the programs, in common programs out there, many of the branches are very well predictable. Okay. There's also some heuristics going on. If you look at the program that looks like this would be a typical layout of instructions in a program that performs a loop. All right. So if this is the branch target for the loop, this would be a number of instructions until we hit this branch instruction, which would look at some condition codes, some branch flags, and then decide whether to loop back here and return to the loop entry. And many CPUs will predict, in the absence of known history, many CPUs will predict that this branch is indeed taken. It will be part of a while loop or of a for loop, and it's much more common for a while loop or for loop to really resume its operation and enter the next iteration. Any while loop will of course sometimes exit at this particular point and execution will proceed here. But this is only happening once for every while loop. All the other iterations are going back to the loop entry here. So it makes sense to predict branches for which we have no further or other history that go backwards in the address space to the top of the loop to predict them as being taken. All right. It's a different story for branches that can exit a particular loop. So think of the break statement in languages like C. Okay. So if the loop is currently in progress and we are encountering this branch that protects the break jump, okay, then it's very likely that the branch is not taken. In almost all of the cases, the control flow will just pass through because we will stay inside the loop and just continue to iterate. Only once in this particular loop, only once in this particular while loop with a break, for example, we will indeed find that the condition is true and that we need to break. In all other cases, it's very probable that we will just fall through and not take the branch. Okay, so that would be the prediction that is performed here by modern CPU. It's really astonishing how good this history and heuristic-based prediction in modern CPUs can work. CPUs invest some storage space to record a history of branches that have been taken or not taken at particular addresses, and can really learn very sophisticated patterns of branches that have been taken and not taken, taken, not taken. Very sophisticated patterns can be learned by modern CPUs, and it's really surprising and astonishing how well the branches are being predicted. And that's a good thing because mispredicted branches are really costly. In the next video, we will run an experiment that can assess the real cost that the CPU faces if it mispredicts branches, if it encounters branches that are hard to predict by nature. Mispredicted branches lead to pipeline flushes, as we said, and instructions that have been started in the pipeline will have to be stalled and then removed from the pipeline. And of course, we will, instead of the subsequent instruction just next to the branch, we will have to jump to some other, probably to a target that might probably be far apart from our actual branch, and that might lead to instruction cache misses because we are surprised that we have to take a branch. This particular part of memory that will hold the instructions of the jump target are probably not in the instruction cache, and we will face instruction cache misses. And cache misses are super costly, as you know. So we will do anything that can help to reduce the number of these mispredicted branches. And writing code in a particular fashion, writing code in a particular way can help to reduce the number of branches inside code. The less branches, the less risk that we mispredict them. And if we need to have branches, then we better only have branches that are perfectly well predictable for a CPU. So get rid of the unpredictable branches, only keep the good and the predictable branches. And there's a number of programming techniques that are around and that are also incorporated inside MongoDB. And we will have a closer look at these quite clever techniques in the next video, we will see that this cleverness can really have a substantial impact on the performance of our selection operations inside MongoDB. Cannot wait to talk about this with you. See you in the next video.